My name is Dewani Patel, and I'm going to be talking about how you can use palladium membrane to increase dual hydrogenation efficiency. And this was done by the Sun Group, specifically under Gudong Lee at the University of Cincinnati. So for some background information, what is hydrogenation and why is it important? So basically, it's the chemical reaction between two hydrogens with another compound, and it's used to convert liquids to fats. The drawbacks of this are that oils that contain trans fats can create complications regarding health, specifically with your cholesterol and your heart, and it reduces the number of unsaturated fatty acids in oil, which are the good fatty acids that you want. The benefits of this is that there's longer shelf life and for saturated fatty acids, higher melting point for saturated fatty acids, and increased chemical stability. So how does palladium help the process of hydrogenation? So palladium improves hydrogenation rate and selectivity, it reduces the upcoming separation cost, and has high hydrogen flux. And high hydrogen flux means the amount of hydrogen recovered. So using these three steps below are involved in the permeation of hydrogen using palladium: dissolution, diffusion, and chemiabsorption. So dissolution is the hydrogen dissolved in the palladium, diffusion is the hydrogen diffused throughout the palladium membrane, and chemiabsorption is the palladium absorbed through the hydrogen of its surface that forms palladium hydride, so the amount of palladium that's recovered. Dual hydrogenation as an alternative. So this is our project. So our main goal is to use palladium membrane electrodes to further enhance the hydrogenation efficiency for various unsaturated organic compounds. So this figure shown above is our setup for electrocatalytic dual hydrogenation using the palladium membrane electrodes. So as you can see on the left is shown the anode, and that's the PD foils that are reacting with the 1 molar KOH with the presence of 0.6 molar HCHO, shown as PDA. The cathode shown on the left is just reacting with the 1.0 molar KOH, that is shown as PDC, which is the cathode. The AEM shown in between is the anion exchange membrane. This allows anions to transfer through, but not cations. As you can see, this is a 4-part assembly. We've talked about the 2 PD membrane electrodes, and then there's 2 chemical chambers, which we'll talk about next. So what's actually happening? The picture on your right shows all the ions that are actually transferring through and the actual mechanisms of what's happening in our experiment. So with the 4 compartments and the 2 palladium membrane electrodes, it's possible for the chemical chamber to independently take place in hydrogenation. Since both chambers are separated, so that's why I was talking about the 2 chambers, by formaldehyde, which is the CH2O, oxidation will occur at the anode. The formaldehyde to formate, which is a reduced form of palladium in alkyne conditions, will allow for hydrogen absorption. The absorbed hydrogen will be able to diffuse through the palladium membrane anode and push forward hydrogenation on the other side of the chamber. So if you start from the right side, it's going to push it through to the left side as well. This assembly also allows for dual hydrogenation outside of the chemical cell, resulting in overall high selectivity. This also produces a low voltage since there is a favorable thermodynamic potential. So you can see that on the outsides there are even ions working to create this dual hydrogenation effect of the palladium and of the hydrogen. So what are the results? The positives are that we save at least 1 voltage of input, we double the hydrogenation rate and the Faradaic efficiency. The negatives are the active site will depend on the makeup of the palladium. Palladium catalysis will directly affect how well the hydrogenation reaction works, and the palladium will be damaged with each use. So how is this actually going to affect us in everyday life? Basically, we are using electricity and water instead of the old method of pressurized hydrogen gas to create with this dual hydrogenation alternative, which has a higher efficiency of hydrogenation reactions. So this will increase with product production for manufacturing and pharmaceutical companies with higher shelf life and less wastage. Since it results in 1 less voltage, they will be able to make more with less energy consumption. In the future, I would like to develop methods to sustain the palladium membrane throughout the hydrogenation process to reuse the palladium membrane to further experimentation. This is a list of references I used to create this PowerPoint. Thank you very much.